Good afternoon to one and all. In this video lecture series of manufacturing technology, we are going to discuss about cutting forces in orthogonal cutting. My name is Divya Kumar, assistant professor from Mechanical Department Engineering from SNS College of Technology, Coimbatore. In the previous lecture, we had already discussed about single point cutting tool nomenclature, orthogonal and oblique cutting, cutting fluids, cutting tool materials, heat aspects, etc. Now we are going to discuss about the cutting forces which is acting the tool during the orthogonal cutting. The force system in the general case of conventional turning process is shown in the figure. First, this is the workpiece, and this is the tool. This is the x direction, y direction, and this is the PZ is the z direction. In case of Px means the axial feed force or thrust force, which is acting in the horizontal plane parallel to the axis of work but in direction opposite to that of the feed. Px is the thrust axial feed force, or it is also known as the thrust force. And this is the Py, that is the radial force which is acting on the workpiece during the machining process. It acts in the horizontal plane along radius of work, that is the axis of the tool. Third type PZ, it is the cutting force or tangential force which is acting in vertical plane and tangential to the workpiece surface. In major, there are about 3 types of cutting force during the orthogonal cutting, that is the axial feed force, radial force, and then the cutting force or tangential force. Next, we will discuss about the merchant analysis. Merchant establishes the relationship between the various forces acting on chip during the orthogonal metal cutting, but with the following assumptions. He assumed that cutting velocity always remains constant, and also he told that cutting edge of tool remains sharp always during cutting with no contact between workpiece and the tool flank, and then chip does not flow sideways. And the next assumption is the only continuous chip is produced during the machining process, and there is no build-up edge for the chip which is produced during the machining process, and no consideration is made on inertia force of chip, and width of tool is always greater than that of the width of the cut. And behavior of chip is like that a free body which is in the state of the stable equilibrium due to action of two resultant forces which are equal, opposite, and collinear. These are all the assumptions of the merchant analysis. Next, we will discuss about what is the machinability. Machinability of material refers to ease with which it can be worked with the machine tool. Some of the criteria to evaluate the machinability are tool life between the grinds, quality of surface finish, power consumption during the machining process, form and size of the chips produced during the machining process, cutting forces, shear angle, and rate of metal removal under the standard cutting conditions. Factors which is majorly responsible for increasing the machinability is chemical composition of tool and the workpiece, and then the microstructure of the tool and the workpiece, treatment given to the metal, that means whether we are given the hot working conditions or it is produced during cold working conditions, and its hardness, ductility, tensile strength, etc. What is machinability index? Machinability of different metals are compared in terms of their machinability index. Machinability index is cutting speed of metal investigated for 20 minutes tool life divided by cutting speed of the standard steel for 20 minutes tool life into 100. This is the percentage of the machinability index. SAE 112 steel 100%, it has a chemical composition of carbon content 0.13%, sulfur 0.08 to 0.03, magnesium 0.06 to 1.10. The low carbon content, it has a low carbon steel of 55 to 65%, copper content 70, stainless steel 25%, brass 180%, aluminum alloys 300 to 1500%, magnesium alloys 500 to 2000%. In case of excellent machinability, magnesium alloys, aluminum alloys, zinc alloys can be added. In case of good machinability, red brass, gun metal, grey, and malleable cast iron. If the material has a poor machinability, example is low carbon steel, low alloy steels, etc. For fair machinability, stainless steel, sintered carbide, high-speed steel, etc. Thank you.